Hey guys, I'm glad you're able to find this video. So today we're going to be starting the chemistry unit, but we're going to be starting with some review from grade 9. So we're going to be looking at writing formulas. If you look at the assignment, this is actually the second half of the assignment. I'll be going over the first half of the assignment probably on Tuesday. So writing formulas. You probably spent at least a week to 2 weeks just looking at this in grade 9, and we're going to be covering this in one day. So writing formulas is when we take the name of a compound and we write the formula that matches that one. So we're going to be splitting this up into 4 different categories. The first overall category we're going to be looking at are the ions. So remember, ions are when there is a positive and a negative ion that are combined. This is also when they give and take the electrons, compared to sharing when it comes to the covalent. So the first one we're going to look at is just simple binary ionic compounds. And don't worry, I don't expect you to memorize the periodic table. I have posted on my Google Drive the data booklet that you'll be allowed. I am also going to be posting these notes on my Google Drive so that you have access to them without re-watching the video. So binary ionic compound. Let's break this down first. So binary means 2. Ionic means there's going to be ions, a positive and negative, and compounds, it just means that there's multiple elements together. So if we're going to be writing formulas, we're going to be given the name. So for this one, let's say we are given sodium chloride. This is actually a relatively common one. If you've had any food today that wasn't just fruit or vegetables, I can almost guarantee you that you've had sodium chloride. This is table salt. So what we do is we look at our periodic table. Sodium is Na, and it has a charge of +1. Chloride, well, that's chlorine. So that has a symbol of Cl and a charge of -1. So there's 2 different ways of looking at this. The first one is called the crossover method. And what we do is we take these numbers and we cross them down. This works for some, but not all. So Na, 1. Scientists, we don't really write 1s down very often unless necessary. So because it's a 1, we leave it blank because it's assumed to be 1. And then Cl, 1 again. So this is how we leave it, NaCl. Like I said, the crossover method works for some, but it doesn't work for all. So there's another way that I like to look at it. So I have my Na 1+ and my Cl 1-. And now what I look at is I look at how many positives and negatives I have and what we need to make for 0 pairs. So I have 1 positive and I have 1 negative. Does that make a 0 pair? Do I need to multiply these by anything? Well, as is, they make a perfect 0 pair. So I don't have to change anything. I can just write them in a 1-to-1 ratio. This does get a little more complicated when we have things that we need to multiply. So let's try that next. Let's do potassium oxide. So potassium, if you look on your periodic table, is K with a charge of 1+. Oxide is oxygen, and it is 0, or sorry, not 0, but O, and it has a charge of 2-. So if we look at our positives and negatives, I have 1+ and I have 2 minuses. So what do I do to make 0 pair? Well, I have to take this positive and I have to multiply it by 2. So if I need 2 of these positives, that means I need 2 of these potassiums. So our formula becomes K, and we always write our ratios on the bottom, 2 for every 1 oxygen. So this is what our answer is. This one, the crossover method, does work, but like I said, it's not good to become dependent on it because it doesn't always work. Take our numbers, cross them over, and then we have K, our 2 from here, O, and our 1 from here, which we don't write down. So that was our binary. Now let's look at our polyatomic. So polyatomic ions. So poly means many, and this means atomic means atoms. So these are going to be things that have more than just our standard 2 elements. We're going to have multiple elements in this. This is also provided on your data table. I wouldn't expect you to have these memorized. There is one positive polyatomic that we look at, and that is NH4 with a charge of +1, and that's called ammonium. Otherwise, all the other ones are going to be in the are going to be negative ions. So let's look at this. First off, let's try one with the ammonium. So let's have ammonium fluoride. So ammonium, like I said already, that has a formula of NH4 with the charge of +1. Our fluoride is F, because it's fluorine, with a charge of -1. We have one positive, we have one negative, that makes our 0 pair, so this one's just going to be NH4F. We cannot separate this 4 out. This polyatomic is 1 nitrogen for 4 hydrogen. This 4 can't just disappear, and that is something that you guys love to do. So you have to make sure that you leave that 4. Let's try another one. Beryllium sulfate. So you'll see sulfate written 2 different ways. You'll see it written with an F, and you'll see it written with a pH. I tend to use them interchangeably. We are trying to go towards just using it as an F, but you will see sometimes on periodic tables it's spelt with a pH. So now let's look at this. Beryllium, where is that in our periodic table? Well, that's Be with a charge of 2+, and sulfate is SO4 with a charge of 2-. So again, I have 2 positives, I have 2 negatives. This one works out to be a 1-to-1 ratio. Well, that one was way too easy. So let's try something a little bit harder. Let's try and do a ammonium phosphide. So ammonium again is our NH4 with a charge of +1. Phosphide, because this ends in IDE, we know that it's an element. There are some exceptions to this. Hydroxide is a polyatomic and it ends with IDE, but for the most part, you'll be able to find the ides on the periodic table. So phosphide is the same as phosphorus. And phosphorus has a charge of 3 minus. So now I have 1 positive and 3 minuses. Well, how do I make my zero pair? Well, I have to take this positive and times it by how many? Well, I need 3 of them, which means I need 3 ammoniums. Okay, now this is looking more hard, isn't it? It's not that difficult. Remember, like I said, we need to have that NH4 together. We can't do anything about it. But I can't just throw a 3 down there because now it looks like I have 43 hydrogens. That doesn't work. So what we do is when we need more than one of that polyatomic, we use brackets. And then I just need one of my phosphoruses. So it would be NH4 and brackets 3 with our phosphorus. Okay. Now we only have one more ionic type that we looked at in grade 9, and that's going to be our multivalent. So multivalent means multiple different valence shells. And if you kind of remember when you looked at Bohr models, valence shells are the outer shell of an atom. So these guys are found in the transition metals, and they have more than one possible charge. So what happens is in the name, you have to tell me what charge you're using. There are quite a few of these. No, we don't just choose the top one. So let's say we are given iron, and when we tell the charge, we always tell it in a Roman numeral and in brackets. So iron 3 oxide. Well, iron is Fe. This 3 here tells me that it has a charge of 3 plus. Oxide is our oxygen with our charge of 2 minus. So now I look at the charges. I have 3 positives and I have 2 negatives. Well, this doesn't work. Even if I add in another negative or another oxygen, now I have one more oxygen or one more negative than a positive. So now I have to add another plus. Okay, now I have 2 more positives than I have negatives. So again, I have to do it again. Ah, we are finally even. So how many irons did we need? Well, we have 2 groups of 3, so we had to multiply that by 2. And how many negatives did we have? Well, we have 3 groups of 2, so we had to multiply this by 3. So when we write it out, it's going to be Fe2O3. So the hardest part about this is remembering that this Roman numeral is giving us the charge. So let's try another one. This one's kind of cool because I'm going to use the exact same elements, but it's going to give me a different answer. So I'm going to use iron 2 oxide. So again, iron is Fe, and this is 2. So this tells me it has a charge of 2 plus. Oxide is our oxygen with our charge of 2 minus. So again, let's look at our positives and negatives. We have 2 positives, we have 2 negatives. Oh, well, do we have to do anything, or is it going to stay as a 1-to-1 ratio? Well, right now it evens out, so it's a 1-to-1 ratio. This is the type of question where doing the crossover method doesn't really work, because if I did the crossover method, I would have a different answer. Take these, cross them over. I would end up with Fe2O2. And I don't really like having both of those two. I kind of want them in the lowest terms. So I'd have to notice this and go, okay, well, if it's 2 and 2, I can divide both of those by 2, and then it can give me FeO. So sometimes the crossing over method looks like it's going to save us time, but it's not necessarily the case. I prefer doing the zero pair method. Okay. Now, we are done all of the ionics. Now we're down to the covalents. So covalent is different because these guys share electrons. They don't give or take, and they are generally nonmetals. So completely nonmetals. So this is going to be things like carbon dioxide. Again, this is something that you guys, it's one all around us, and every time you exhale, you're exhaling carbon dioxide. So the key with this one, if you haven't noticed, is that when we are doing covalent naming, we are using something called prefixes. And prefixes tell us how many of that atom there are. So carbon, well, that's just C. And we don't even have to look at the charges for these guys. Dioxide, well, oxide is our oxygen, and di means that there are 2 of them. So this formula is literally just CO2. The reason why I know there's only one carbon is because we don't have a prefix there. If there is no prefix before the first one, it means that we are going to just have one. But how do we show if we only have one for the second one? Well, that's as easy as doing something else that you guys have probably heard of before, carbon monoxide. So mono means one. So again, there's no prefix before the carbon, so I know that I just have one carbon. Oxide is our oxygen, and because it says mono, we only have one oxygen. So this formula is going to be CO. That's it. It's a 1-to-1 ratio. You're going to see things that can get quite high. We don't usually go higher than about hexa, which is 6, but we usually give you guys up to 10, which would be deca. This could be something as easy as, how about this? Di, nitrogen, trioxide. Okay, so the first thing we do is we separate out our prefixes. So nitrogen is our N, and di means how many are there? Well, there's 2. Trioxide, oxide is our oxygen. Tri means, well, think of a tricycle, there's 3. So this formula is N2O3. So if you look at your assignment for this section, like I said, the first half is taking the formulas and naming them. I'm going to be doing a separate video on that. But the second half is being given the names and writing the formulas. I'd really like you to try those questions out, and then for now, just snap a picture and email me your assignment, but you can hold off on that until we finish the second video. I hope this made sense. If you have any questions, please send me a message on Remind or email me. Hope you guys are staying safe.